think it's a case of rain, stop, learn. I don't know, has bad weather, has there ever been an excuse for people not coming to their lectures and learning? I suppose, if it was raining, people wouldn't come because it was wet. If it was sun shining, they wouldn't come because it was nice weather outside. Welcome to this afternoon's Digital Trust and Security Talk, part of our Digital Futures Programme. Essential points, hopefully the signage outside will be relatively clear if you need to follow it, because this is going to be, this will disappear in a moment. Point out where the toilets are, no fire alarms planned, so if one goes off, just follow me running down the corridor. Hopefully I'll find the right way and won't lead you astray. There will be photographs taken. If the kind of work that you're involved with requires you not to have photographs, or like me, your jacket doesn't match your trousers, then please have a word with Kitty and she'll make sure that those photographs aren't used in property material. If you're really worried that then there is a risk assessment done on request, usually involved, if I talk too long, then the mask will drop from the ceiling. So if we can show where the loose slide is, they're on here somewhere. Can anybody see them? Oh, there we go. Look, yeah, there seems to be lots of them, usually hidden behind lifts for some reason. And I've just discovered, on the opposite end of the spectrum, there's a nice water cooler around it, but leave time, because they've done the marketing. I've noticed it's called a Niagara water dispenser. And believe me, if Niagara Falls trickled like that, nobody would ever visit there. So, was that all the official stuff I need to talk about? Cool. Right. Who's heard of the Northwest Cyber Corridor? Not very many. There is a Northwest Cyber Corridor. It's really actually quite exciting. It's a sort of a join the dots. Some people map it from GCHQ in Manchester to the upcoming National Cyber Force in a place called Samlesbury. Who's heard of Samlesbury? One or two people have heard of Samlesbury. I highly recommend it. It's got a fabulous nature reserve called Brockholes. Great day out if you like that kind of thing. Perhaps not on a day like this, though. Maybe not. There's not a lot of shelter. But it does have a floating cafe, which is a really interesting way that they've made land. That's not, of course, why we're here today. The other way to look at the Northwest Cyber Corridor is the fact that in there are 3 academic centres of excellence for cybersecurity research. Ourselves, Liverpool, and slightly further north, we've got Lancaster University as well. So making a titanium triangle of strength in cybersecurity. The reason why I particularly mention this is because it's good for people to know that that kind of activity is going on, because we believe in collaboration and co-creation, particularly in this kind of space. And the Digital Futures Programme is a really good example of that kind of stuff, because we really need the expertise in all the different areas and the different faculties, schools and departments when it comes to that. So it's good for you to know about the Cyber Corridor, but it's also because of the Cyber Corridor that I first met David, who suddenly started talking about IP version 6, which is one of those things, I don't know, how much do people know about IP version 6? IPv6? 1 or 2 people, and it's on the borderline thing. For me, it's always one of those things where I feel, yeah, I ought to know more about it, and it's always the next thing I'm going to read, but something else always comes up in between. So when David offered to come and talk about it, I metaphorically bit his hand off. And I think it's really, really important because of the different sorts of knowledge you really know. Not necessarily to know about the details of security, but to have a really good idea of who it is you need to include in your conversations. So you might think your area of whatever application of technology or science, from medicine to engineering to civil or whatever it might actually be. The important thing of making sure that that is going to run reliably and securely and be trustworthy and all that kind of stuff relies on so many different people's input. Again, kind of the philosophy between mapping out the Northwest Cyber Corridor. The thing that sort of strikes me about IP version 6, 1943, what was everybody doing in 1943? Not even I was around in 1943. Thomas Watson? Name mean anything to anyone? Pop quiz time. Who was Thomas Watson in the 1940s?
Oh, great guess.
Good guess, but he was head of IBM. was head of the IBM, and he ranked in one of the worst predictions ever when it comes to technology, because it was in 1940p, he reckoned that the world would never have a market for more than 5 computers. And that would be fine, wouldn't it, when it came to inevitably, presumably, connecting those 5 computers up. You know, we don't need to number them from 0 to 4. That's a computer science joke. Never mind. I suddenly realised, actually, my filing cabinet, I did this subconsciously, my filing cabinets all have 4 drawers. And the numbering system, I numbered them 0 to 3. It was only when I put the stickers on afterwards that I noticed it. So sometimes you do these things automatically. But in terms of giving names, you know, when you run out the names of Star Wars characters, and Muppets and Dungeons and Dragons characters, being able to name or address a particular piece of equipment, we're all getting quite nicely along with this internet protocol, which is numbered version 4, in terms of saying, right, that's the address, that's the device you need to be talking about, whether it's a computer, whether it's whether it's a camera, whether it's a microphone, whatever connected technology you're actually talking about. And with hospitals having thousands of pieces of technology, we soon started running out. Now, I understand, and David might cover this, that IP version 6, it's a bit like sort of these biblical things saying sort of your progeny will be more than the stars or the sands of the desert and all that kind of stuff. But we don't need to worry about naming them or addressing them, because IP version 6 will cover that. But like so much technology, nobody's really thought about security right from the beginning, which is a shame. Well, you can look at it either that's a shame or it's a great opportunity, because that's probably the reality of the job that people have. So there are security issues that you need to think about, not insurmountable security issues, which is good, but it's an area that I'm interested in. It fits in really well with the Digital Futures Programme that looks at everything from online harms through to far more technical subjects as well. So I'm really thrilled to invite David to enlighten us about the risks and opportunities of IP version 6, and you may well have devices on your desk and your pockets already which are using it, just guessing.
Yeah. Well, hey. So yeah, thanks Tony, that's it's a really good introduction. And yeah, I'm David Kennedy, I'm co-founder of Arkenox, and basically we specialise in IPv6 security solutions. My background as well is originally in threat intelligence, so finding things that are issues before they actually turn into issues, which is a theme that I'll carry out for this presentation. Cool. So everyone loves a bit of public participation. We have got a slider just to make it a bit more interesting. So there's a couple of questions as we're going through. It's not a test, it's nothing to catch you out, it's just to basically get your views on a couple of things. And you can either join now, or again when the questions come up, the code will reappear. So yeah, let's give everyone a couple of seconds. But yeah, it'll flash back up again later on if you've missed it. So, cool, let's get started. So quite a bold statement. Could IPv6 be your biggest cybersecurity oversight? It's pretty bold. And oversight for one or two reasons as well. Is it oversight because of the risks, maybe that you're not paying attention to? Or is it also an oversight because there's possibly benefits of IPv6 that we're not making use of? And this is something that we're going to cover in this presentation. The one thing with IPv6 though, is it's a bit like digital Marmite. So there's a group of people who love IPv6, want it deployed everywhere. There's another group of people who hate IPv6, don't want it anywhere near their networks. And there's actually a third option with Marmite, which often gets forgotten about, and that's a group of people who, you know, what on earth is Marmite? And in this case, what on earth is IPv6? So when we talk about IP, it's the Internet Protocol. And basically what the Internet Protocol is it's the language of the Internet. Every device has got an IP address, and it's how they can communicate with each other, send data to each other. So it's, you know, absolutely critical to how the Internet functions. As with all languages though, we've got to make sure that we have an Internet Protocol that scales to the size of the Internet and also to any new use cases that we might have. And if we look at spoken languages, back in history, quite a lot of spoken languages died out purely because they could not scale to new use cases or, you know, different things. So that's pretty key for the Internet Protocol. Yeah, and where to send data. So there's two main types of IP, and Danny covered these really well before. We've got IPv4, and you know, these might look a bit more familiar. the types of IPv4 addresses we've got. If you look on the back of your router at home, you'll probably see one of these. And we're going to class this as the legacy version of the Internet Protocol. And then we've got the new version, which is obviously IPv6. Addresses look a little bit different. We'll go into this in a bit more detail. But what often most people think now is they go, hang on, we've missed one out. We jumped straight from IPv4 to IPv6. What happened to IPv5? Well, it did exist, although very briefly. It was basically developed at a very similar time to IPv6 was. And we decided that IPv6 solved more problems, had better potential. So that's where the development of IPv6 continued. And IPv5 basically got dropped into the sidelines. Cool. So before we can break into what IPv6 is and why we literally have it, it's worth looking at IPv4, and that will start to basically, some of the problems we have will start to come out. So again, it was standardized in 1981, and we have in total 3.7 billion public IPv4 addresses. So from that, you might already see the problem that we've got. Back in 1981, when the internet, was still pretty, not very well widely used, we thought, we've got loads of IP addresses there, we can assign these to all the devices we've got. We've got plenty of availability. But the problem is now, is the internet's a pretty common thing. Everybody uses it. We've all got plenty of devices we want to connect to the internet. So we've started to run out. And if you think of that as, what, about 8 billion people in the world now? So that's not even one public IP address per person. Fortunately enough for us, a while back, we started to see this problem coming, and we thought, okay, we're going to implement some mechanisms to actually prolong the life of IPv4 so that we don't just grind to a halt when we're trying to expand the internet. And basically the main mechanism we use to do that is something called network address translation. So a bit of an example of it down here. If we've got the University of Manchester, which sits on the internet, that's using a public IPv4 address. And then we've got our devices, say in this room, that we want to connect to the University of Manchester with. Well, in between us and the University of Manchester, we have a router. So there's literally some bolted to the ceiling now. That has most likely also got as well one of these 3.7 billion public IPv4 addresses. The key bit here, though, is that for these devices to connect to the internet, they have to go via the router and network address translation. So these devices get what's called a private IP address. And this is the key bit. So when these devices want to connect with the University of Manchester, the University of Manchester sees that IP address. It doesn't see the IP addresses of these devices behind it, which means that these devices aren't directly connected to the internet. In a way, we get a layer of security from our network address translation because they're sort of disguised behind it. And that's a really key theme of this whole presentation right there, that in IPv4 we do get a sense of security through private and public IPv4 addresses. Cool. So when we look into the internet in 5 or 10 years' time, what type of things are we going to have there? Well, Internet of Things is going to be pretty big. We're going to want to connect, as I lawnmowers to the internet, whatever else. Blockchain as well might start getting pretty popular. Again, these are all things that want to interconnect with each other. We're all going to need IP addresses. So can IPv4 continue to support that, given that we're running out? Well, short answer is no. And actually back in 2019, this was from RIPE NCC, so they're the ones who basically govern the internet for Europe. They announced back in 2019 that we ran out of IPv4 addresses. So that's it, the supply's done. There's no more public IPv4 addresses to go around. So what does that mean then? If we want to keep on growing our digital networks, well, we can join the waiting list. And the waiting list is pretty long, and you have to wait a long time. So 502 days currently you've got to wait for. And the key bit about this as well is that the organisations in this queue are big organisations. They're the likes of BT, Sky, and most organisations will never get a look into this. So they can never be part of this queue to get more IPv4 addresses when they come up. So what can regular organisations or users do? Well, we can use network address translation if we wanted to. We can continue to juice that last remaining bit out of those public IP addresses we've got. But this is getting far more difficult to do. So when we look at things like video conferencing and stuff like that, they are quite intensive from a NAT point of view. So it's becoming harder and harder to connect more devices behind our NAT gateways. So you want to set up some sort of service, put it on the internet, or you might go to your hosting provider, spin up a little VPS, whatever else. And then you get given basically a public IPv4 address to do that with. But you basically gamble on the history of that address you get given. So say you get allocated an IPv4 address, and then say one day you don't need it anymore, the company takes that back and you give it to somebody else. So in the history of that IPv4 address, it's distributed malware, maybe it's been involved in phishing attacks, things like that. Then the history of that IPv4 address is going to follow it around. It's called basically poisoning IP addresses. So if you were to inherit an IPv4 address that has previously had some sort of bad history, then what you might see is users actually can't get to your address. And this has actually happened recently, quite recently. There's a couple of big organizations who've spent a lot of time, a lot of money developing these web apps. They inherit an IPv4 address that's been poisoned, and then they wonder why their clients can't actually view it. And it's because they don't trust this IPv4 address because of the history it's had. And this is something which I don't think people realize is actually going on. Because the supply is so reduced and the demand is still quite high, there's now a full-blown marketplace for IPv4 addresses. And you can see some of the size figures that are going around, right? So /13 is a massive IPv4 address base. There's a lot of addresses there, but somebody wants $20 million for their IPv4 address allocation, so there's big sums of money going around. And the organizations basically involved in this are legacy, so educational establishments, BBC, Department of Defense, people who are involved in the internet right in the early days who got these massive IPv4 allocations. They're now going, well, hang on, they're actually worth quite a lot of money now, so let's begin to sell them or lease them out. So, first question, if you want to get involved, and if you're really good at maths, you might have been able to work it out from the previous slide, but what do you basically think the current value of an IPv4 address is? So when you're talking to your ISP, whoever else, you've got that IPv4 address, how much is it actually worth if you want to go and sell it? Right, I'll give a few seconds or something. And fingers crossed this works as well, because I wasn't playing ball the other night. Cool. Give it like 10 more seconds or something. Yeah, we'll go for it from there. Cool. Okay, interesting. So the actual value is about $34. It did used to be higher back in about 2020, but the price is actually slowly increasing again. And this is something that organizations start to factor in, that if they need a lot of IPv4 addresses, well, there's costs associated with that. Cool. So hopefully we've seen that these mechanisms we've put in place to prolong life IPv4 aren't really long-term solutions. So what is the long-term solution? Well, that's why we're all here, it's IPv6. So the main benefit we get with IPv6, and Danny introduced this a little bit as well, was in IPv4 we get 3.7 billion public IP addresses. In IPv6 we get that many. Right? So if you're anything like me, as soon as the number goes past about 1 trillion, I'm just like, that's a big number. And the way that I visualize this, and this comes back to Danny's example of you going to like Cosmic or whatever, is if you took every grain of sand on Earth, and you made an Earth for every single grain of sand, and then over all those Earths, count every single grain of sand, and once you've got that number, times it by about 5, and you're getting close to that number there. So what does that ultimately mean? It means we can give public IP addresses to every single device that we've got today and those of the future. So it means we can continue to expand the internet. And with IPv6, this is where the differences start coming in from IPv4, because we don't just give one IP address to a device. We can give multiple. They have different types as well, different lifetimes. But if we were to go by the book and go by best practices, we actually give an entire massive subnet to every single device for IPv6. And it's a /64, so it's a huge number of IP addresses. And that gives us flexibility. So this is the example IPv6 address. I know it looks complex, it looks complicated, but if we break it down into its individual parts, it starts to make a bit more sense. So say we're an organization, we want to use IPv6. Where do we go to? Well, we could go to our internet service provider, someone like BT. And what BT would do is they'd turn around and they would give us this bit highlighted in black here. So this prefix, they would say, that is your IPv6 address allocation. You can do what you want with it. So we've got this big range of IPv6 addresses. Well, what do? We start to divide it up based on our use cases. Maybe we've got different offices, different teams, things like that. So we start to divide this up with something called subnet IDs. And then everything after that is what we'd allocate to devices. So when I was saying before, we give a whole chunk of IPv6 addresses to each device. Well, that is the size of the chunk we would give. So this IP address, it ends in EF01. If we were to change this to EF02, that's a new IPv6 address. EF03, a new IPv6 address. And if you think if we kept on iterating this number up for this whole orangey red bit, that is the amount of addresses that every single device would get in IPv6. So it's a huge quantity, it's a huge amount. Yeah, there we go, that's explaining it a bit more. So again, if we take this and we look, what can we do? In IPv4, it's a little bit fragmented how we might set up our network. Maybe it's not particularly logical. Well, with IPv6, again, we can do this fragmentation. So we can divide it down into subnets based on what our use cases are. And quite often what I hear when people say, what they don't like about IPv6 is they just don't want to remember that size address. They can't remember it. They can, don't really like remembering IP addresses anyway. So how are we going to remember IPv6 addresses? Well, basically all you need to know is that is our prefix. So if we see that anywhere in IPv6 address at the start, we know it's us. And then when we start to break this up, if the thing that follows our prefix is a 1, we know that's London office. If it's a 2, it's Manchester office. If it's a 3, it's infrastructure. And then we can go down even further than that and say if we have some sort of, threat comes in that we get alerted to, and we see that it ends, it's got 22 after the prefix, we can look pretty quickly and go, well, it's got 22 after the prefix, therefore it's the guest network in Manchester. So that's how we can start to basically work out quite quickly, based on our IP addresses, where stuff lives. The other thing we can do as well, if we've got this hierarchy, is we can implement network-based filtering, access control lists, whatever else at each level. So say for the Manchester office, we might put in certain rules that govern the whole Manchester office. And if someone was to come and add a new subnet down at this level, then straight away it adopts those rules that we implemented higher up in the hierarchy. So that's something that can basically make it a bit more scalable. So again, with IPv6, it's known as a bit of a glacial technology in that it has been around since 1988. And in 2015, it managed to get to 5.5% of internet traffic. So this is according to Google as well. The Google stats are pretty good because for somebody to reach Google with IPv6, not only does their device have to support IPv6, their router needs to support IPv6, and their internet service provider needs to support IPv6. So that's why Google stats are pretty good to working out what IPv6 adoption is. So in 2015, we finally got to about 5%, which is pretty slow. It took us 27 years to get there. So the next question obviously is, if in 2015, IPv6 adoption was 5.5%, what do we think global IPv6 adoption is today? Right? Do we think it's basically carried on, maybe linear? It's gone to maybe 8%? Do we think it's 1 in 5? Do we think it's near half? Do we think it's nearly everything? And this is according to Google as well. So depending on where you look for your stats, there is difference, but I've used the Google stats for this. Cool. Give everyone a couple of seconds. Yeah. Five more. Let's go for it. Cool. Okay. So according to Google, 46% of their traffic is now using IPv6. There's the rest of the graph. In the UK, it's a little bit higher than that. It's 48%. US, it's now over half. And when we look at countries like France and even India, vast majority of their traffic is using IPv6 now, over IPv4. And I've added this in as well to say that they're seeing a decrease in latency, which if you're an organization where time is literally everything, maybe you're in some sort of low latency trading, whatever else, where if you can get a couple of milliseconds over your competitors, migrate to IPv6 because you can get reduction in latency there. So why has the rate of IPv6 adoption increased? And this is stuff which sometimes people don't know about, is IPv6 is enabled by default on nearly all operating systems now. So this is Windows since Server 2008, Windows since Vista, Mac OS, loads of the Linux distributions, mobile operating systems, all natively support now IPv6. In the case of Windows, it goes a little bit further, and if a Windows device has got access to both IPv4 and IPv6, it will actually choose IPv6 now over IPv4. Which again, if you're looking from a cybersecurity point of view, maybe you're an attacker. Well, attackers love default configurations, and also they love things that they control, so preferences and things like that. Our major internet service providers, especially in the UK, are now offering IPv6 connectivity. So BT, Sky, Vodafone, the UK Educational Network, Janet, all offer IPv6. So we have our devices that support IPv6, most routers support IPv6, and then we've got our internet service providers who also support IPv6, which gives us that connectivity out to the internet. Another interest as well, so cloud. Cloud service providers in the past couple of years have made massive sort of leaps towards supporting IPv6 in all their different services. And they've actually gone so far as to in the past year they've started charging for using IPv4. So if you use a public IPv4 address in cloud service providers, you end up paying for it. So if you can wean yourself off IPv4 and use IPv6 instead, then you can start to save some money. And there's basically one more reason, this is a pretty big reason as well, as to why the adoption rate has grown, is government mandates. So China, this is massive. By 2030, every single device in China is going to be IPv6 only. All of them. So from 2030 onwards, IPv4 is gone in China. And they are being really aggressive in chasing this as well. So they've actually started publicly calling out individuals who are holding up the progress. I've seen some stats recently where they reckon 600 million users in China are now IPv6 only, so they will never use IPv4 again. There's other countries as well, so Vietnam, Germany, India, have all got sort of mandates and things like that in place. And the other main one as well is the US. So there's a federal mandate in there where by the end of this year, 80% of devices in the federal agencies are going to be IPv6 only. And this mandate goes one more as well and says the remaining 20%, or anything that can't migrate to IPv6, there needs to be a plan in place for how that is decommissioned. In total, there's more than 60 different nations that have got mandates or programs in place for IPv6. And the most important bit of this is the UK is not one of these. So you might be thinking, right, we're off the hook. It's okay, UK's not got a mandate in place, we're all good. But that doesn't matter because we're now being dictated to. If you're an organisation who maybe has suppliers out in China, maybe you're an organisation which deals heavily with the US federal agencies, well, the thing is here that IPv6 and IPv4 aren't natively compatible with each other. So if you don't support IPv6 in some sort of form, then you're going to lose connections to these partners and suppliers and whoever else you've got in these countries. So that's what's driving this adoption forward. Basically, the outcome of all this is IPv6 is already everywhere. It's already on your devices, it's already being used by suppliers. Most websites, major websites that we're going to use, are already using IPv6. And the key bit here is whether you know it or not. And from a cybersecurity point of view, that's the key bit. Cool. So you might be thinking, well, hang on, where's IPv6 basically come from? We've not deployed it in our networks, so how's it got there? When IPv6 was first sort of looked at and developed, we looked at IPv4 and went, well, IPv4 is quite manual. It's quite manually intensive to set up. So what can we do with IPv6 to basically solve that? Is we can use auto-configuration. So IPv6 has got a feature called stateless address auto-configuration. What it basically does is if we took a device and dropped it into a network that supports IPv6, that device can configure itself to get that IPv6 connectivity. So how does it do that? Well, if we drop this device in, it generates what's called a link local address. And it normally uses some form of its MAC address. It might randomly generate this, but they always usually start with FE80. So that's how you know you look at a link local address. And with this address, it basically gives it that local access to the network. I've also highlighted here as well some, if you're an attacker, types of things you could do with this. So once it's got that link local address, it reaches out to its local network. And it basically says to all the other devices local to it, has anyone else got this link local address? This is the link local address I want to use, is anyone else using it? And that's because we need those unique addresses to communicate. Obviously, from an attacker's point of view, what they could do is if we've got a device that's saying, is anyone using this address, I want to use it, an attacker could reply to all these requests and say, yeah, I'm using it. It tries again with a different link local address, the attacker replies, yeah, I'm using that. And you end up with basically a bit of like a denial of service situation where the device can't configure itself on IPv6. So once we've got that link local address, we've got that local connectivity, we know it's unique. It reaches out and says, is there any routers there who I can communicate to the internet with? Again, an attacker could get involved with this. Again, the attacker needs to be local in the network as well. This is the key bit. But if there is a rogue router in your network, attackers could reply to these requests and say, yep, I'm your router. You need to communicate with me, and I'll get you connected out to the internet, which can create like a bit of a covert channel. Maybe it bypasses all your monitoring and things like that you've got in place. But basically what happens is the router replies to the device. It gives it that allocated IPv6 address space. And from that, the device picks an address out of that space, and that's what it uses to get connected to the internet. And this is the key bit, right? If it can configure itself on IPv6 automatically, are you monitoring that? Do you even know there's devices that are doing this in your network? Okay. Another bit of technology which is pretty good to mention is that a network can have both IPv6 and IPv4 connectivity at the same time. If an organization says they're using IPv6, normally they've got what's called a dual stack configuration. So they're running both IPv4 and IPv6 at the same time. And what that basically means is an organization can support devices that still only use IPv4, as well as supporting, say maybe they've got their suppliers out in China who are IPv6 only. So that's why you tend to sort of have a dual stack configuration. It means you can still communicate with everyone. So if we go back to our basic network diagram we had before, we see now University of Manchester is offering IPv6 connectivity, and our router as well has got an IPv6 address. So what happens when we drop a new device in? Maybe this is a little Windows server, something like that, which prefers IPv6 if it's got the option of IPv6 and IPv4. It goes through the process we had on the previous slide, and it gets itself an IPv6 address. The key bit here, and the key difference is that when this server goes and communicates with the University of Manchester over IPv6, the University of Manchester sees the server's IPv6 address. So it means what we have now is end-to-end connectivity, where if you don't have the required filtering, maybe the required access control list, it means that anything else on the internet that's using IPv6 can come and access our server, and vice versa. So, yeah. Double R attack surface area as well. If obviously we've got two types of connectivity running at the same time. Don't imagine at the same time. Yeah, and this is pretty important as well. So sometimes people don't want full IPv6 connectivity in their networks, so what they use is like translation mechanisms to be able to run IPv6 and IPv4 or vice versa. And quite often we don't even include those in our security controls as well. So there's all these different avenues that attackers can basically exploit and leverage. So IPv6 is designed to be around for at least the next 100 years. And you know, if we do run out of IPv6 addresses, the main thing is none of us will probably be around to deal with the, what we have to do after that. So it has to account for use cases of today and also use cases of the future that we've not even thought about yet. So I don't know if everyone can see that. I know it's a bit of a small diagram. But basically what we have is the IPv4 header was quite complex. If we wanted to do any sort of niche use cases, whatever else, we embedded that directly into the IPv4 header. Whereas with IPv6, we've stripped loads of those options out. It's nice and clean. It means we know what we're going to get. When we get an IPv6 packet, we know that the header is going to look like that, which is cool. And if we want to add those options on, we use something called extension headers, where we basically bolt on extension headers after the IPv6 header. We'll go into this in a little bit more detail later, because from a cybersecurity point of view, there's some stuff we can do here. But concept's great, because it provides flexibility. But as with flexibility, provides opportunities to attack it. So that's what we'll go into in a couple of minutes. So we've gone through why we've got IPv6, what are some of the benefits of it, and things like that. Well, you know, what does it actually enable? So when we're looking at future use cases of the internet, Internet of Things, blockchain, if you go and look at Bitcoin in 2011, right, in the early days of Bitcoin itself, they actually removed IP to IP connectivity. One of the possible reasons for this, or well, one of the reasons, is because of network address translation. If I want to send Bitcoin to somebody else, and we're both hidden behind network address translation, we can't really verify the identity of each other. Whereas with IPv6, it's end-to-end connectivity, so we can both see each other on the internet. With crypto and blockchain and everything else in IPv6, there's so many opportunities there. I think that's going to be something which is massive. IoT, so already people have started building on top of IPv6 for IoT-specific use cases. 6LoWPAN, so this is basically low power. If we've got sensors maybe scattered up the side of some sort of mountain, we can use 6LoWPAN, and that basically enables it. Means you don't have to go and change the batteries, whatever else. And the other thing we do with IPv6 as well is create mesh networks. So we're no longer just reliant on those specific pieces of networking kit. IPv6 can also configure itself, so if the routes that it was using suddenly go down, it can configure itself and still find ways how to transmit. We've looked at this as well, so obviously we've got our hierarchical networks that we can understand a little bit more. But we can do things as well like temporary addresses. So we spoke before how we expose our IPv6 address to the internet. But because of the size, the number of IPv6 addresses each device gets allocated, it can basically iterate through those. So if we were to communicate with the University of Manchester, it might create an IPv6 address for that session, and as soon as that session's done, it gets rid of that address, which basically gives that device privacy because the address it was using technically no longer exists. As well, we're at university, so what research has gone into this? Well, there's been quite a lot of research, and I've put the sources down at the bottom. What this research basically found was that on an IPv6 network, you are 14 times less likely to receive email spam when compared to IPv4. I think it's still 90% of all compromises come from phishing emails. So if you can reduce that, that's great. Two possible reasons for this. One, cyber attackers haven't migrated to IPv6 yet. But the other reason is as well, if you want to send email over IPv6, there's a couple of extra checks that go on to validate the source. So that's a cool benefit. And the other one as well, if you receive a lot of bot traffic, if you place blocks using IPv6, and well, key bit is if you get those blocks right, you can massively reduce the impact that traffic causes. And there's another bit as well to this, that there's less collateral in IPv6 blocks too. So right, let's get on to the juice of it. The security issues of IPv6. So when we look at IPv6 as a technology, it's not necessarily new. It's been around quite a while. And what this basically means is people have configured it in dribs and drabs over a long period of time. What were the best practices 20 years ago aren't the best practices today. The people who configured IPv6 20 years ago might not be still working at the same company. And those devices that were configured might still be connected to the internet all the time. We then have continued to expand on top of IPv6, usually without a consistent plan. Sometimes the best practices changes, so we do different things. And then there was all things, and Danny introduced this before, security is always usually an afterthought. Or at the time this was configured, maybe the tooling we had didn't support IPv6. So what does this basically lead to? It leads to areas of oversight that attackers can start targeting, can working out. And ultimately, you can't protect what you don't know. If you don't know about something in your network, you don't know what your devices are doing, how do you go about protecting it? Cool. So basically, I've listed IPv6 as more of a front door than a back door. In cybersecurity, we talk about back doors quite often. We want to protect ourselves from these backdoor compromises. And that's what we've been really busy doing. But well, with IPv6, this is how we connect out to the internet. This is how your attackers would connect to you. And in the case of IPv6, we've forgotten about it. And in most cases, we've just left IPv6 wide open and unmonitored. And a question that I ask, when we look at cybersecurity, we do audits, right? ISO compliance, payment card information compliance, cyber essentials, for example. Maybe you have pen test done. Well, have they included IPv6 in that? Because most likely it's being used in your network somewhere, so you should probably include it. And basically to bring all this together, this is the cyber kill chain. It's basically whenever you've got a cyber attack, you can chop that cyber attack up into 7 stages. And the idea is you want to stop those attacks right at the early stage. The later that those attacks progress, the more damage they're going to cause, the more expensive it's going to be to clear them up. The thing we can do with IPv6 is with just IPv6 we can progress into these latter stages of the kill chain. So normally you'd have to bolt together loads of different technologies to progress, whereas with IPv6 we can do that first chunk just with one technology. So reconnaissance is the start of all attacks. Well, how do we perform reconnaissance in IPv6? So it should be really difficult. We've seen the size of the address space means we can't just brute force it. IPv4, you can brute force through every single possible IPv4 address. I think the going rate is you can do that in about 4 minutes now. IPv6, you can't do that if you follow best practices. But the thing is, when people have developed their IPv6 networks, they've gone and used sort of non-optimal addressing strategies. Maybe they've gone and used things where they embed the MAC address of the device into the IP address, so you can basically derive what the IP address will be. Out of the massive address space, maybe they've just used the very start of it. And then this is quite a good one, this service exposing addresses. So seeing this all the time, where an organization might have a device that is running SSH. So to remember that that device is running SSH, they'll say it's 22 at the end because SSH runs on port 22. Attackers are well aware of that, and you don't want to be exposing your SSH servers and things like that to the internet. So yeah, that's how people basically would perform reconnaissance against IPv6. And this is actively going on. Reconnaissance of IPv6 is actively happening. And that's the rule of thumb, right? If it's easier to remember, attackers are going to go and find it. But the main thing is, if we use these addressing strategies, we've got to filter like we would in IPv4 to protect them. I'm just conscious of time as well. So we spoke about extension headers, and that we daisy chain extension headers on when we want to use them. This is basically what we end up doing. The problem here is there's no sort of fixed rules around the amount of extension headers we can add into an IPv6 packet. And our networking equipment is pretty bad at processing IPv6 headers. Normally it will only maybe process the first 3 extension headers, and if it's anything more than that, it will just either say, yep, just let the packet through, which from an attacker's point of view is jackpot time, or it might say, I need more time to process this, so it punts that packet into the general purpose CPU, where if you send enough of these packets at a router, it starts to clog up the CPU, can bring down the network and all this sort of stuff. So yeah, that's a pretty good attack vector. Again, it just comes down to understanding your network. Do you even need extension headers? What extension headers are you even using? Which ones do you expect? Anything else? Get rid of it. You're not expecting it. And then third parties and supply chains. So you might think, well, as an organization, we're not going to deploy IPv6 for whatever reason. Well, it doesn't matter because we're so heavily integrated with other companies now that they're enabling IPv6. So Microsoft have just quite recently enabled IPv6 for all of its Exchange Online customers. There's millions of organizations have suddenly now got exposure to IPv6 that they might not be aware of. And even then, I've seen this quite often. Organizations turn around and say, well, we've disabled IPv6 on our devices, in our networks, whatever else, which is really hard to do, just disable IPv6. Again, Microsoft come around and they say IPv6 is now a mandatory part of Windows. And if you disable IPv6, there might be things that stop working. And as we become more integrated with IPv6, as more services start relying upon IPv6, then you can't keep on disabling it. It's not going to work. So, final question is coming to the wrap up a little bit now. So, it sounds like a bit of a trick question. There's no right answer, there's no wrong answer. Based on what we've looked at today, between IPv4 and IPv6, currently, do you think IPv6 networks are more secure than IPv4? It's not a trick question. I'm not going to be like, Cool. Oh, it's catching. 50-50 split? Yeah. Okay. So I think that was no, just about.
Like Brexit.
Exactly, there we go, pretty much bang on. But basically the whole outcome of all of this is we need to understand our IPv6 networks to the same level we do as IPv4 before it's too late. And if we keep on ignoring IPv6, if we keep on not understanding the risks, not including it in our audits, well, what happens? That attackers will understand our IPv6 networks better than you do. And when that happens, you've lost. And we had a warning last year, so back in last August, there was a vulnerability that got released in Windows. And it's debatable as to whether it actually impacted IPv6 or not. But the fallout from that was we saw on social media, everyone just started saying, disable IPv6 to mitigate this vulnerability. But in the future, as IPv6 becomes more deeply integrated, maybe we've got suppliers who we need to communicate with IPv6. We can't just panic disable IPv6. So that's why we need to understand our networks now. Yeah, I mean, I hope you found that useful. Might have generated more questions to go away and look at. We've got a little LinkedIn page as well, so if you search for Arkenox or if you search for myself and connect with me, that'd be great. But yeah, any questions?
I'm going to ask a question of the audience, and maybe it'll bounce back.
Cool. Yeah.
To you. Particularly because you've mentioned LinkedIn there.
Yep.
Right. Anybody follow any of the security discussions on LinkedIn? No?
In general or?
In general. Have you noticed there's a particular trend that as soon as a security incident happens, what do all the experts say on blame on LinkedIn? Bit of a trick, bit of a sense of humour type question.
I'd say to use it.
Okay, I'll have words with you afterwards. Everybody from humanities, take this guy outside. Anyway, they always blame DNS. It's always DNS, you know. So the question I want to bounce back is sort of the way that addresses are handled for IPv6 and changes, and somebody makes a change and you've got to wait a day or two for things to roll out. Is it essentially the same system, or is it better, or is it worse, or is it? I mean,
it's essentially the same system. And when IPv6 was basically developed and created, the idea was that it would fit quite nicely into our already existing protocols and things like that we use. Yeah, I think that's just what a lot of people don't realise, is that when you communicate to a website that supports IPv6 over DNS, then quite often it will use IPv6 because it will either be lower latency, so it will pick IPv6, or in the case of Windows, it'll pick IPv6. So, yeah. Hope that answers the question. Yeah. Go on, Anthony.
Very interesting.
Yeah.
I didn't realise it started in 1985.
Yeah.
So, yeah, it shows that adoption of technology doesn't always go at the speed of light.
Yeah, slow.
And IPv6 has been around for a long time because, as you said, we're going to go around the
Yeah.
thing, and we haven't.
Yeah.
Because IPv4 still works because of NAT.
It does. It does.
So, businesses are probably quite happy behind that.
Yep.
So why change?
That's a great point. It's a great question. Because as we saw as well with network address translation, you almost get, I'm not going to call it security, but you get obscurity by default. That your devices are hidden behind this NAT gateway, which, from an organisation's point of view is great. I think the change will start coming in when they are basically told to start adopting it. When their suppliers in other countries and things like that start using IPv6 only, and it's like, panic time, we're going to have to also start looking at IPv6. Or when the cost of using IPv6 starts going up. So maybe their internet service provider, whoever they're using, starts charging more for IPv4. Something we see as well is certain organisations who've got big allocations of IPv4 have actually funded their IPv6 deployment by selling IPv4 addresses. So that's where, from a business's point of view, if they say, right, there's a cost associated with deploying IPv6, if you can mitigate that by selling IPv4, that's something which, the execs and things like that will probably sign off because there's not really a full cost.
Well, the danger not, if suddenly people go to IPv6
Yep.
and they're not as secure as they are with IPv4,
Yep.
you then get more organisations become victims,
Yep.
and then they've got to blame the technology.
Yeah, and this is the main risk, because then when that happens, you probably migrate to IPv6 because you have to, and then all these security threats start showing up, and you can't almost go back. Because if you were to go back and disable IPv6, then the whole reason why you migrated stops, if that makes sense. So that's why we almost just need to get ahead of the curve now, understand what your exposure is. Does your security tooling support IPv6? Quite often it doesn't. Is that on the roadmap for those vendors? All that sort of stuff.
I'd like to counter the gentleman's proposal of it being less secure, because by default, routing and firewall is now based on everything in, regardless of the course technology comes in on.
Yeah.
So even if you've got your device behind your gateway,
Yeah.
an IPv6 address, your firewall, if it's recent or relatively recent, should be smart enough to allow traffic to flow in the direction you configure it.
Yeah.
And out of the box, default, you're saying nothing can come into my network unless I've got an established connection outbound, and that's in the same for IPv4.
Yeah.
Even with an IPv6 address, if you establish a direct connection, you're still firewalling your devices, assuming you've got those gateways where you use a consumer device.
Yeah.
design to roll that out anyway.
Yeah.
Or you use enterprise hardware.
Yeah, and that's enabled by default. So if you go to your home network and it's using IPv6, if you go into the config, it will say, block unsolicited inbound.
So the other thing that I think really not necessarily discussed, but I don't know how popular it is, but most of our phone vendors, I think Verizon in the US is IPv6 only.
Yep.
And I don't think any consumer would have known that would be the case, and they're not necessarily the type you're going to see on the devices.
No.
Still being prompted to install applications.
Yeah.
That would be the main malicious vector.
Yeah.
I think treating IPv6 as vulnerability is just kind of like saying, look, it's a bit scary.
Yeah.
Because there's lack of understanding there.
It's true.
It's just a transport protocol, and
Yeah.
it's just signpost of the internet of DNS.
Yeah. I think, so with the routers and things like that, what we've seen especially is when people have configured IPv6 to reduce the amount of debugging and things like that they've gone and done, they've gone and turned off those default settings in their routers and never put them back on. So that's where you end up just exposing your devices to the internet.
Because you've got the almost like the apprenticeship style teaching in certain organisations.
Possibly.
The elder senior engineers don't just use IPv4 because it works, that's all I know.
Yeah.
Because there's not been that learning, that
Yeah.
cascade of learning down from continuing education or from
Yeah.
development.
And people don't like change as well. So if somebody knows their IPv4 network inside out and suddenly we're saying, right, we're going to add IPv6 to that, there's almost that bit of a blocker that people don't want to do it. Yeah, but certainly when we've seen reconnaissance, and reconnaissance is happening, that is looking for these exposed IPv6 addresses, exposed for whatever reason, and maybe you can actually get a device to communicate with you first to create that connection, and then maybe you can go and exploit it. But yeah, so that's another thing to add as well, that those security issues that were raised, there were bits of, you might have seen an RFC and then a number after it. So a lot of the security issues in IPv6 you can actually have already been looked at. There are already basically solutions out there for how you can stop these security threats. So the question at the end I put up where it said, currently are IPv6 networks more or less secure than IPv4? Well, there's the opportunity with IPv6 that if we were to build it using best practices, were to integrate these additional methods of privacy into it, to build a network hierarchy that we understand and we can implement these rules at different levels, we could actually have a network that is far more secure than IPv4, just by default. That's my opinion anyway, but yeah. It's a great question, yeah.
Just a question from, I think I'm going back some of those years.
Yep.
But I remember part of the proposition for that IPv6 was by default we had IPsec.
Yes, so...
I don't know if that's debunked, or the way it's been
So,
what we do now with IPv4.
That's a great question. I was debating whether to include it or not, that when you go and ask people what's the main security benefit of IPv6, especially if you go and ask something like, one of the AI models, it spits out IPsec, and IPsec was mandated back in the early days of IPv6, but has since that mandate's been removed. So IPsec is no longer mandatory in an IPv6 network. So you could still add it if you wanted to, but it's not a major benefit purely because the uptake of IPsec was so low that it was dropped out of being mandatory in IPv6 network. But yeah, no, really good question, really good question.
Any other questions?
So why did you say that IPsec was dropped?
So there was an RFC that proposed adding, well, basically said that IPsec should be included in your IPv6 network. There's since been one, I can't remember it off the top of my head, I'll dig it out, that basically said that because the uptake of IPsec is so low, that it's no longer required for an IPv6 network. So the latest best practice for an IPv6 network is that you don't need IPsec.
But if you form part of IPv6, wouldn't benefit everybody because it would be a better connection?
I guess.
More secure for everyone?
Yeah. Yeah, it's just getting people to adopt it. Same with a lot of the...
That means that who rules is not just in other people's security, is it?
Possibly. It's a good comment though. Why was it, taken out of being required?
A lot of VPNs dropped set as well.
Yeah, I think so. Yeah.
So
What?
a lot of VPNs have dropped its IPsec. They stopped using it. The big VPN providers.
Basically to create space for mitigate for exploitation.
It was great for maintaining connectivity, but a lot have just dropped it and they're starting to use.
And so with the extension headers piece as well, a lot of organisations just drop extension headers. You send any extension headers, they just get dropped. So even then, if you're using something like IPsec, and you're against an organisation that just drops any extension headers, you know, IPsec wouldn't even get through. If that makes sense.
So what are the alternatives then? In that case?
Using things like privacy addresses, putting in access control lists, filters, all that sort of stuff, making sure you've got proper monitoring and things like that in place. Any other questions? Have we got time?
Another question at the back.
That's me, wasn't it? Are you aware of any initiative from Janet, for instance, to persuade the council and universities that they might adopt these six?
I think they do have.
Well, this is outside boundary physics, which
Yeah,
basically
CERN, isn't it?
by CERN.
Yeah. I think they do have a program where they will do training, I think, last time I looked, to educational establishments. I'm not too sure. I know about the CERN situation that, you know, they've got like a really mature IPv6 network now, and that obviously spans to other organisations too. Yeah.
All right, fantastic. Well, firstly, this is not the end of the conversation.
Nope.
I don't think you're rushing off.
No.
Unfortunately, but obviously left all the contact details. I think just before you think about giving a big thank you to David, I think you should give an extra special thank you to David. I don't know whether Kitty has any awards, but actually, do you realise this is possibly the first technology talk that I've come to for a while, where it was 2 minutes to 3 this afternoon before David mentioned AI. So I think he needs a special thank you for that. Thank you very much.
No, thank you to yourselves as well, and Kitty, for organising. Yeah.
Not at all. Sorry, just trying to get to the end of the
Oh
presentation.
It's a long one.
Yeah, we've got some connections to some of the other pieces of the jigsaw in this field. They are, like I say, they have they're, you know, right from the deep dives up to the to the generalizations. Really useful, and yeah, please use the feedback thing as well, so that Kitty can tailor the program to what people need. I was going to say thank you for coming out in the rain, but it looks like you're going to be rewarded because you're going to be able to go home in the sunshine. Fantastic. Thanks ever so much.
No, thank you very much. Cool.
I thought that was probably my colleague saying, "Where are you?"
Yeah. But it's all right. Slido worked. It wasn't working the other day. Couldn't get it working, so yeah. So it's quite well.